Well, we finally finished doing all of our review. Now today we can start 3.1, which is limits, and it's the start of actually doing calculus. Limits are absolutely fundamental. They form the foundation for all of calculus. And we'll start off, I won't tell you what a limit is to start with. I'll sort of motivate this with a question. So here's our function. We consider the function f of x is going to be x minus 2 over x squared minus 4. Right, a nice rational function. The question is, what value, if any, does f of x approach or get close to as x approaches or gets close to the value 2? And the first thing I'll note is your first instinct might be, well, if x is getting close to 2, why not just let x equal 2, right? So note, what happens if x equals 2? Well, then I'm evaluating f of 2. So you plug 2 into this, you get 2 up top, so 2 minus 2 over 2 squared is 4 minus 4. Well, that's 0 over 0, and that doesn't make any sense, right? So this function is undefined at x equals 2. Right, it's a rational function, but it's discontinuous. 2 is not part of its domain. It's discontinuous at x equals 2. It's not even defined there. But that's okay, right? The question is not what is f of 2. The question is what happens as x gets close to 2. Right? Not actually at 2. At 2 we've determined it's undefined. But what happens if x gets close to 2? Well, one way you could approach this is just start plugging in some values. Right? How about I let x get close to 2? So I'm going to make a table here. Let's take some values that are close to 2. I'll take x less than 2 for starters. Did I leave myself enough space? We will see. So here's our value for x. We'll plug in 1.5. Alright, so 3/2. That's pretty close to 2. Plug it in. You'll need a calculator for this. I've already got the values computed. If you plug in 1.5, you get about 0.2857. Well, unfortunately, just this single value doesn't tell me what value f of x approaches as x approaches 2, but I suspect it's probably pretty close to 0.2857. Although if I form a sequence here of numbers closer and closer to 2, I might notice a trend. So let's go something closer to 2. How about 1.9? Right, 1.9 is definitely closer to 2 than 1.5. So we'll plug in 1.9. Plug 1.9 to this function. You get 0.2564. Okay, can I recognize a trend yet with 2 values? Not really. How about we get even closer, right? 1.9 isn't all that close to 2. We could do even better. Let's plug in 1.99. Really close to 2 now. And if you do that, you get 0.2506. Now I'm starting to notice a trend, right? It certainly looks like as x gets closer to 2, these values are getting closer to 0.25, right? It looks like it. Let's try and verify that. Let's get even closer to 2, right? 1.99, it's close to 2, but we can do better. Let's go 1.999. If you do that, you get about 0.25006. Well, that sort of really confirms our trend now, right? It certainly looks like as x gets closer and closer to 2, these values are getting closer and closer and closer to 0.25. So I'm pretty convinced now, but you could play this game forever, right? If you don't notice a trend, keep plugging in values. Go 1.9999, right? Get very, very close to 2. One thing though is I've only looked at values for x less than 2, right? I've only approached 2 sort of from values less than 2. What if I approach from the other side? What if I came in values bigger than 2? So let's try and do that. Let's take x bigger than 2 and look at function values. So we'll take 2.5, plug 2.5 into this function, you get about 0.222. Alright, 2.5 was close to 2, but we could do better, right? How about we go 2.1? Do that, you get 0.2439. Certainly looks like it's doing what I would expect. You're approaching 0.25, but let's try and verify this. Let's get even closer. about 0.201, or sorry, 2.01. Plug that in, you get 0.2494. Well, that's really close to 0.25 now, right? But we'll go one step closer, 2.001. Really, really, really close to 2. And we're looking at 0.2499. So what does this look like to me? Well, it looks like exactly what we've already said, right? It looks like as x gets really close to 2, you can't plug in 2 because the function's undefined, but as you get really, really close to 2, it certainly looks like the function values are getting closer to 0.25. And one way of denoting this is you could say f of x approaches, there's the arrow to indicate what it's doing, it's approaching 0.25 as x is approaching the value 2. And there's a notation that some people use. This is totally fine notation. I don't think we'll use this too often in this class, but it's really nice shorthand notation that intuitively tells you what's happening, right? It says, as x is approaching 2, this function is getting really close to the value 0.25. Actually, at 2 doesn't matter, right? So there's another way of writing this. Right? So there's one way of indicating that as x approaches 2, the function approaches the value 0.25, but I call this section limits, and people tend to use limit notation instead. So if f of x is the function we had to start with, x minus 2 over x squared minus 4, we write, you could write that, but more commonly you'll see this. You'll see the limit as x approaches 2 of x minus 2 over x squared minus 4. So this is read as the limit as x approaches 2 of this function. And it means, what value does this function approach as x approaches 2? And as we just saw, it looks to us like it's 0.25. Right? So this is our notation. And formally, this is what a limit is. A limit is this idea of the function is approaching a particular value as x approaches a particular value. Doesn't say anything about what happens actually at x equals 2, right? We don't care about that. Limits don't care about the function at x equals 2. It's what happens as you get close to x equals 2. And I would like to indicate this graphically. If I drew the graph of this function, right, if you go into Wolfram Alpha or something and you plugged in this function, you would see, let's see, what does it look like? So left. You would see this. Okay, I've got an asymptote there. This is happening at x equals minus 2. If you graph that function, here's x equals 2, you would see it looks like this. So here's the graph of y equals x minus 2 over x squared minus 4. So yeah, this is a very nice looking function, right? There's nothing too wrong with it. There's this vertical asymptote at x equals minus 2, this discontinuity right here, where the function is not defined. But otherwise, the reason we can't plug in x equals 2 is because it's not actually defined right there. It's got this hole in the graph, right? It's got a discontinuity right here. But that's okay, because you can still ask what happens, right? As we saw when we plugged in values for x that are really, really close to 2 from the left, or really, really close to 2 from the right-hand side, we were getting these function values, these y values up here on the curve, and these y values were getting closer and closer and closer to 0.25. I should probably dot that out. Alright, so this is what we were doing. We were plugging in values for x that are really, really close to 2, and we were observing that these y values are actually getting closer and closer to this hole that we're skipping. Right? And again, so we used our limit notation. Right? We used our limit notation. The limit as x approaches 2 of x minus 2 over x squared minus 4 equals 0.25. And this is important. It's important that you recognize that limits don't care about what happens at 2, right? That's not what we're asking. This isn't what limits do. It's asking what happens as you get close to 2, right? Really, really, really close to 2, what's happening there? And in a very strong sense, this is what calculus is all about. Calculus is the study of very, very, very small things, right? So instead of asking actually at 2, we're saying just move a tiny bit away from 2, right? Move your x value a tiny bit away from 2, and then what happens, right? And as we saw, if you move just a tiny bit away from 2, the function is about 0.25. Right, so this is what calculus is about. It's a study of very, very small things. Alright, so just to be completely clear, right, here's three functions I'll draw. Here's a nice function. Here's number 2. Basically the exact same function, but I'll put a hole in it right there. And number 3, basically the exact same function. I'll still put that hole, but I will actually define the function right here to be that value. Okay, so there's the hole occurring right around there. Let's say that's A, and let's say this value is L. So this is A, and this is L. And again, that's happening at x equals A. There's L, and let's say this value is H. Okay. There's our 3 functions. I've called them all f of x, but they're all slightly different from each other, right? So in this case, if I asked what's the limit as x approaches a of f of x, well, this one's pretty easy, right? You look at this, okay, what happens is x is getting really close to a, well, you're moving along this curve, and your function values are getting closer and closer to the value L, right? So the limit here exists, it equals L. What about this one? Limit as x approaches a of f of x. Well, here this is like the first example we had, right? The x minus 2 over x squared minus 4. As x is approaching a, as you get closer and closer to a, you're moving along this curve. You're getting closer and closer to L, but you never actually get there, right? Because the function's undefined at a, so it's not actually, you never actually equal L as you plug in values for x that are closer and closer to a. But still, this is the question the limit is asking, is it's not asking what happens at a, right? It doesn't care about what happens at a. It doesn't care that there's a hole right here. It's just asking what value do I get closer and closer and closer to? And in this case, it is, in fact, getting closer and closer to L, right? So our limit exists, and it equals L. Last but not least, what about this one? What happens now? X is approaching a, I get closer and closer to a, so I'm moving along this curve, and now the function's actually defined at a, right? It's actually defined to be h, so f of a is h, but once again, that has no bearing on a limit, right? Limits don't care about what happens at a, they care about what happens as you get close to a. And in this case, as we get closer and closer to a, the value of the function is getting closer and closer to L. So all 3 of these limits are the same, right? In this case, the function's defined to be the value a, or L at a. Here it's undefined. Here it takes on a completely different value, h. But in all 3 cases, as you get close to a, they're all approaching L. So all of these limits are the same. Here's a classic example. It's a warning that, okay, we're talking about limits now. What happens to the function as you get really close to an x value? What happens to your y values? And in all these cases, we were evaluating the limit or indicating what the limit equals, but they don't have to exist. So limits do not always exist. That's a wonky exclamation point. So for example, consider, I'll call it h of x in respect for what's usually called the Heaviside function. This one won't be quite the Heaviside function, but it'll be close. Well, it'll be the value all the y values will be negative 1 if x is less than or equal to 0, and it'll be positive 1 if x is bigger than 0. And the question will be, what's the limit of this function? What's the limit of h of x as x approaches 0? Well, one thing you could do is you could just draw this. So let's draw this function. Here's y equals h of x. And what do we have? If x is less than or equal to 0, it's always the value minus 1. So let's say this is minus 1 down here. And so it's always minus 1. There's the x-axis, by the way, and the y-axis. And actually at x equals 0, it's defined to be negative 1, so I filled in this circle here. And then above, for all positive x values, it's defined to be positive 1. At 0, it's not positive 1, but everywhere to the right, it is positive 1, right? So there's positive 1. So there's the graph of this function. It's negative 1 for all negative values of x. At 0, it's still negative 1, but then once x goes positive, it jumps. It jumps, so we've got this jump discontinuity, and it goes on as positive 1 thereafter. All right, so the question is, limit as x goes to 0 of h of x. What is this? Right? So this is asking, as x gets closer and closer to 0, does my function approach a single fixed value? And in this case, you'll observe, well, okay, if I approach 0 from the left, and if I come into, if I let x approach 0, my function is approaching the value negative 1, right? Meanwhile, if I let x approach 0 from the right, come in this direction, what value is my function approaching? It's approaching the value positive 1. Right? So there is actually no single fixed value that the function approaches. From the left it approaches minus 1, from the right it approaches positive 1. In this case, you have to conclude that the limit doesn't exist. Right? So this guy does not exist. Forevermore, if a limit doesn't exist, I'll just write dne, right, shorthand for this. And this is because h of x is not approaching a single fixed value as x tends to 0. However, what we've talked about here comes into something very naturally of the concept of a one-sided limit. So what we do have is we have right-hand limits. Sometimes it's interesting to talk about this. Right-hand limit and left-hand limits. And for this function, these actually do exist, right? So we've talked about coming into x equals 0, coming in from the right, right, for positive values of x. And this guy exists, and the way you denote this is you say the limit as x approaches 0, and the way you indicate it's a one-sided limit is you superscript the 0 with a plus. Right, so I'm coming in to 0 from values bigger than 0 of h of x. And what does that equal? Well, as we agreed, as x approaches 0 from the right, my function is getting closer and closer. In fact, it's always equal to this value, but it's getting closer and closer to positive 1, right? So this guy exists, and it equals 1. Meanwhile, the limit as x approaches 0 from the left, how do you indicate from the left? Well, you superscript the 0 with a negative sign of h of x. What does that equal? As x approaches 0 from the left, right, coming in from the left-hand side, what value we're getting closer and closer to? We're always equal to it again, but we're getting closer and closer to negative 1. So the left-hand limit exists, and the right-hand limit exists. And this is why the full limit doesn't exist, right? This is why this limit up here doesn't exist, is because the left and right hand limits aren't actually equal to each other. That happens pretty often. It's the prototypical case of one of these jump discontinuities where the function jumps up in value. And if the left and right hand limits don't equal each other, then the full limit doesn't exist. If they do equal each other, then that's the value of the limit. Okay, so just to make sure we really understand how all this stuff works, here I've drawn a function with a whole bunch of stuff going on. There's points of discontinuity and jumps and whatnot. And I just have a whole bunch of pieces that will fill in. Right? So the first question is, what is the value, what is f of 0? Well, you come to this function, you look at x equals 0, right here, and you ask, what's the function value? Well, the function is usually defined by this nice curve here, but it has a jump. It's got this hole at 0, where it jumps from -2 up to +2. That's the function value, right? So f of 0, +2. What about the limit? The limit of this function as x approaches 0 from the left. Right, so we come into 0 from the left, we move along this curve. What value are we approaching? Well, we get really, really close to the value -2. Right, so this is -2. Next, what's the limit as x approaches 0 from the right? Okay, so come into 0 from the right, move along this curve. Nothing out here really matters, it's just what happens if you get really, really close to 0 down here. And as we get really, really close to 0 from the right, we're still approaching this value -2. The left and right hand limits are the same, so our full limit actually exists, and it's -2. Right? As you approach 0 from either direction, you're approaching the value -2. Okay, I've got this next bit a little bit out of order. Let's jump to h. What is f of 1? What's the function value at 1? Well, it's filled in right there. So our function value at 1 is y equals 0. What about these other limits? What happens as x approaches 1? So we're approaching 1 from the right. Well, you're moving along this curve, and your y values are getting really, really close to, as x gets close to 1, y values get really, really close to 0. So our right-hand limit is 0. What about the left-hand limit? As you get really, really close to 1 from the left, so you're moving along this piece of the curve, as you get really, really close to x equals 1 from the left, you're getting closer and closer to this hole right here. Right? So you're actually getting closer and closer to -1. So the left-hand limit is -1. And last but not least, g. What's the full limit? What's the limit as you approach 1 from either direction? Well, our left and right-hand limits don't agree, right? That means that this full limit must not exist. Be any. And you'll see problems like this. I believe there's a homework problem that looks exactly like this, just with a different function where you have to evaluate a whole bunch of different limits. I will say one more thing before we move on to actually algebraically finding the value of limits. Infinite limits, let's consider this function. Consider the function f of x equals 1 over x squared. Alright, so 1 over x squared, if you were to graph this, it looks like this. Should be more symmetric than I've drawn it, but imagine it's got this reflectional symmetry across the y-axis. So here's x and y. Here's the graph, y equals 1 over x squared. So obviously it's undefined at 0, right? It's undefined in x equals 0 because that causes division by 0. But the question is, what's the limit as x approaches 0 of this function? 1 over x squared. Well, the only conclusion you can make is What value does this function approach as x tends to 0? If I were asking you as a class, you'd probably give me two different answers. One, and the really rigorously mathematically correct answer is it doesn't exist, right? Why? Because there's no single fixed value this function is approaching as x gets closer to 0, right? It just keeps getting bigger and bigger and bigger and bigger, right? So this does not exist. There is no single fixed value that this function approaches. And the reason there's no single fixed value is because infinity is not actually a mathematical number, right? It's not part of the real number line, it's not a number in itself. However, limits often fail to exist because of something like this, because the function blows up in a particular direction, off to positive infinity or negative infinity. So often we write limit as x goes to 0 to indicate something like this, of 1 over x squared. In this case, it's not a terrible thing to write that this limit equals infinity. Right? If you wrote that, anybody would understand what you mean. You're technically saying the limit doesn't exist, but it fails to exist in a particular way. It fails to exist because the function is blowing up to infinity. So unless something is specified where it says, if a limit is equal to infinity, say it doesn't exist, either one of these would be correct. In fact, I believe it usually goes the other direction. If a limit doesn't exist, but it doesn't exist because it blows up to infinity, actually indicate that it equals infinity. All right, so I sped through that part of the video because this took a long time to write, and what we want to do now is, I've shown you graphically, right? I've drawn graphs of functions, and we've looked at graphs and said, okay, the limit equals this just based on a geometric interpretation of the graph. But what we want to do is go back to the very first example we did, right? The function was x minus 2 over x squared minus 4. And actually evaluate limits like that algebraically without having to plug in a whole bunch of values, right? We plugged in a whole bunch of values closer and closer to 2. There are nice ways algebraically to evaluate limits without having to go through that process, right? So the goal is I give you a function and you tell me what the limit is as we approach a particular value. And the start to that process is knowing our limit laws, right? So assume that as x approaches a, the limit of f of x and g of x actually exist, right? So these are defined. Then if you take the limit as x approaches a of the sum of these two functions, right? Maybe one is like e to the x and the other is 5x, so e to the x plus 5x. Well, if you have a limit of a sum of functions, you can break that up into a sum of limits. So you can evaluate the limits separately and then add them together. Second rule says if you have subtraction, you do the same thing. The limit of a difference of functions is the difference of the limits. Thirdly, right, limits are actually really nice operations because of these first three properties. If you have a limit of a constant times a function, c times f of x, you can pull that constant outside. That's just c times the limit of f of x. Similarly, 4 and 5, 4 says if you have a limit of a product, f of x times g of x, then you can break this into a product of limits. I want to remind you that these properties require that these individual limits actually exist, right? So these two limits have to exist in and of themselves. It's quite possible that you break it up and you find that one of these pieces doesn't exist, but this original limit did, right? So you have to be careful. And last but not least, if you've got a limit of a quotient, f of x over g of x, you can break this up into a quotient of limits. Limit of f of x over limit of g of x. With one additional catch. This limit down here on the bottom, that can't be 0, right? A limit is a number. This is asking what number does g of x approach as x approaches a. If that number is 0, then you have a problem. Then you're dividing by 0. So we'll do examples with the limits or these limit rules in just a moment, but there are actually more of them. I'm going to keep going. I'm going to give you a few more. All right, a few more rules. I know this seems like a lot of rules, but really they're just exactly what you would ever want to do, right? So this says that everything you would ever want to do with limits, you basically can do. So going on with these rules, if you've got the limit as x approaches a of a function raised to the n, well, notice that it's really just this base that's changing, right? As x goes to a, just the base changes. So all you have to do is figure out what the base is approaching, take the limit as x approaches a of f of x, and then raise the whole thing to the n. 7 is essentially the exact same property. If you interpret an nth root as to the power of 1 over n, then it's really just the same property as number 6. It says just figure out what the inside is doing, take the limit of the inside, and then take the nth root of all that. 8 is one I don't usually give, but I believe there's a homework problem that looks just like this. So if I've got the limit as x approaches a of some constant b to a function f of x, so maybe it's like b to the x squared or something, then all you have to do is take the limit of the exponent and then exponentiate b, right? So take b to the power of that limit. And 9 is a really big thing. I'm sort of jumping ahead a bit here because the next section is continuity. We haven't really talked about continuity a whole lot, but I'm sure you've heard this word before in lower level math classes. And 9 is a huge deal. It says if your function is continuous at x equals a, and in truth almost all the functions we work with in this class, being continuous is the same as just being defined, right? If it's defined at a point, it's going to be continuous there. So if it's continuous at x equals a, then the limit is just the function value. So I've stressed over and over again that limits don't care about the actual function value, right? It's not about what happens at x equals a. But this says if you can plug in x equals a, right? The functions we work with, I just give you f of x equals some expression, right? A linear function or a rational function or an exponential function. If you can plug in a, if it makes sense to do so, if you don't divide by 0 or take square root of a negative number or something, if you can plug in a, then that's the value of the limit. Because the functions we work with are usually continuous where they're defined. They don't have jumps or holes or anything like that. So that's a big deal, and we'll do an example in a second. Alright, for example, evaluate the limit as x is approaching 1 of x squared plus 2x plus 1. So I'm going to do this two ways. One is I'm going to do this extremely formally using our limit laws, right? So our limit laws say, alright, I'm taking the limit of a sum of a bunch of functions, so I can break it up into a sum of limits, right? This would be the limit of x squared, I don't really need brackets at this point, limit as x approaches 1 of x squared plus the limit as x approaches 1 of 2x plus the limit as x approaches 1 of 1. Okay, so what's this? Well, one of our limit laws says, in fact, if I'm taking limit of x squared, what I can do is just take the limit of x and then square the whole thing, right? And then this guy, I've got a limit of 2x. Well, that's a constant times x, so I can pull the 2 outside and take twice 2 times the limit as x approaches 1 of just x. And then last but not least, the limit as x approaches 1 of 1. And yeah, I think that's about as far as I can formally push this. Now all you have to know is what's the limit as x approaches 1 of x? Well, x is a nice continuous function. I can plug in 1. So clearly, as x approaches 1, the function x is approaching the value 1, right? So this is just 1 squared. What about this thing? Well, this is also as x approaches 1 of x. As x approaches 1, x is approaching 1. So that's a pretty easy limit too. It's 2 times 1. Now a limit like this quite often throws students off, but if you think about it, right, really think about what this is a function 1, right? Meaning, doesn't matter what x is, x can be any value at all, the function always equals 1. So as x approaches 1, what's the function equal? It's always 1. So it's approaching the value 1. And this is just 1 plus 2 plus 1 is 4. Now I will never evaluate the limit like this ever again in this process because it's way way more than you need to, right? I'm just demonstrating the limit laws here very specifically, but what I would usually do is look at this function, x squared plus 2x plus 1, ask myself, can I plug in x equals 1, right? Do I divide by 0 or anything? No, right? Just plugging in x equals 1, I would get 1 squared plus 2 times 1 plus 1. Same answer, 4. Alright, so if you can plug in the number, if you don't divide by 0, plug it in. That's all you have to do. Alright, we'll do one more. Evaluate the limit as x goes to 0 of x squared minus 9 over x squared minus x minus 6. So again, step 1, if you really want to follow limit laws very precisely, what you could do is break this into two limits. Limit as x goes to 0 at the top, x squared minus 9, over the limit as x goes to 0 of the bottom, x squared minus x minus 6. And then the top and the bottom, you can keep breaking these up, right? I've got a limit of a difference and a limit of a whole bunch. You can break these up, but we don't really have to go that far. By the way, the bottom, I better make sure I'm not dividing by 0 in this limit. But at this point, these are easy limits, right? I can plug in x equals 0 to both of these expressions and nothing happens that's bad. So why not just do that? Plug in x equals 0 at the top, we get minus 9. Plug in 0 to the bottom, we get minus 6. So minus 9 over minus 6 is 3/2. Or technique number 2 would be just ask yourself right away, can I plug in x equals 0? And the answer is yeah, I can plug in x equals 0. So just plug in x equals 0. And once again, you get minus 9 over minus 6, which is 3/2. And based on these last two examples, you might start thinking, limits are really easy. All I have to do is plug in the value. Well, no. We'll do one right now where you can't just plug in the value, right? You'll divide by 0. Here's a good one. It's the very first one we had today. Limit as x goes to 2 of x minus 2 over x squared minus 4. We've already guessed that the limit was 0.25 or 1/4 based on plugging in values that were really, really close to 2. But what if I wanted to do this algebraically? Well, notice I can't plug in x equals 2, right? If I plug in x equals 2, the function is undefined. So the idea is, let's do some algebra. Let's manipulate this first. Do some algebra. Right, let's try and figure out why we're dividing by 0, and maybe we can get rid of it. Right, so notice that the bottom here is a difference of 2 squares. That factors. So I'm going to factor the bottom. This is x minus 2 over x minus 2 times x plus 2. Okay, so same exact function. Well, hold on now. Up top, everything's multiplied by x minus 2, right? Think of this as x minus 2 times 1 if you want. And everything down below is multiplied by x minus 2. So those cancel, right? And this function can actually be written in a much more simple way. It's just 1 over x plus 2. Well, now can I plug in x equals 2? Yes, right? The reason I couldn't plug in x equals 2 before was because of this factor. This x minus 2 factor is what was causing me to divide by 0. Now that I've canceled it out, there's no problem plugging in x equals 2, right? So if I just go ahead and plug in x equals 2, what do I get? I get 1/4, or 0.25. Again, I almost never use decimals, but because we had 0.25 in the first time we did this, I'll write just 0.25 again, right? Which matches up with what we thought the first time around. So these are the harder limits to evaluate. The limits where you can't just plug in the value because you end up usually dividing by 0. And the way you fix it is you do some algebra to cancel factors out. So here's another one. I'm going to change up the notation a little bit. Instead of using x, I'm going to go to h. As you go on to section 3.3, you'll see why this limit looks exactly like limits we do in section 3.3. Evaluate the limit as h goes to 0 of 2 plus h cubed minus 8 over h. So once again, I cannot just plug in h equals 0. That causes division by 0. But what I'm hoping to do is maybe cancel out that factor somehow. So I'm going to do some algebra. The only thing I can possibly hope to do here is maybe expand the top. So we'll cube this out. And cubing things out actually takes a little bit of time, unless you know something called the binomial theorem. So I'm just going to write down the cube here. Check it if you don't believe me. This cube is 8 plus 6h squared plus 12h plus h cubed. Alright, so that's what I get when I cube this thing out. Minus 8 all over h. Well, this is actually pretty good. This 8 here cancels with this 8 here, right? Plus 8 and minus 8. And on top, everything now has an h in it, meaning I can factor out an h. So this is h times, how about I write it in decreasing powers? So pulling out an h from this guy gives me h squared. Pulling out an h from this guy gives me plus 6h. Pulling out an h from this guy gives me plus 12 all over h. And now this problem of dividing by 0 goes away because it cancels. So we're taking the limit as h goes to 0 of h squared plus 6h plus 12. That's now a polynomial in h, right? It looks like x squared plus 6x plus 12, but my variable is h. And there's no problem with plugging 0 into this, right? So I can just plug in 0. Plug in 0, what do you get? You get 0 plus 12. So this limit is 12. And you'll see when you go to 3.3, when you start talking about instantaneous rate of change, this is exactly what those limits in 3.3 look like. Alright, I'm going to do one that's a little bit trickier. Just one more. It's the limit as x goes to 0 of the square root of 4 plus x minus 2 over x. So again, I cannot plug in x equals 0 because I divide by 0. What now? In the first two examples we've done, or the last two examples we've done rather, what do? We tried to factor, right? We tried to factor somehow to cancel out this thing that's causing us to divide by 0 on the bottom. And that's your first go-to technique, but in this case, there's really nothing I can factor. And what I want you to do is recognize this specific type of problem. I have a square root on top. I've got a square root on top minus something. What do you tend to do with square roots? You tend to rationalize. So that's actually the trick I'm going to use here. I'm going to rationalize the numerator. So we're going to take the top, let's rewrite it. We're going to take the conjugate of the top, and we're going to multiply the top and bottom by that conjugate. This is just this trick, this rationalization trick tends to work really well, especially for limits that look like this. If you've got a square root plus or minus something. Alright, so we're going to rationalize the numerator. And what do we get? So up top, this is a difference of two squares factorization. So square the first term, you get 4 plus x minus the second term squared. 2 squared is minus 4. All over the bottom. X times square root of 4 plus x plus 2. Something really tempting to do here is to distribute the stuff on the bottom, but remember, this x is causing me to divide by 0. It's what I want to cancel out, so I might as well leave it factored. So what do we have up top? 4 plus x minus 4, these guys cancel, right? And I'm just left with x up top. This is great because I've got an x times everything on the bottom. 4 plus x plus 2, and now those cancel. They cancel out. So this pesky x that caused me to divide by 0, it's gone. And I have the limit as x goes to 0 of just 1 over the square root of 4 plus x plus 2. And now, plugging in x equals 0 is not a problem, right? This is completely well defined for x equals 0, so plug in x equals 0. What do I have? 1 over the square root of 4 plus 0 is the square root of 4 plus 2. 1 over 2 plus 2 is 1/4. Alright, so there will be several of these types of problems for homework where you have to evaluate these limits algebraically, and this is the tricks that you want to use, right? So try and factor, try and cancel, do some algebra in general to manipulate your expression and cancel out this thing on the bottom that's causing you a problem. And one trick is rationalization, another is just factoring and canceling, and so on. Alright, so this video is getting pretty long at this point. I'll try and make this quick. In truth, a lot of calculus textbooks at this point, they break up what I'm about to do into a different section because it really does become a lot of limits all at once. But this is limits ad infinity. So here's just a very basic function, y equals 1 over x. What happens, my question is, what happens as x gets very, very, very large? Right? Well, what if I take x equals 10? Well, what do you get? You get 1/10. Right? Take a bigger value for x. What about x equals 100? What do you get? You get 1 over 100. Take a bigger value. 1 over 1,000, 1 over 1,000,000. Right? There's really no end to this. Take bigger and bigger and bigger values for x. I don't even have enough zeros here in my million. What is this doing? Well, 1/10, if you want to think of it as decimal, is 0.1. This is 0.01. This is 0.001. This is 0.00000001. Do I have enough zeros there? I think I need an extra one. In any case, the trend is clear, right? As x gets bigger, my function is getting smaller and smaller and smaller and smaller. Right? And that's because, once again, if you graph this, the relevant portion of it, clearly, as x gets smaller and smaller, the function is approaching 0, right? As x gets bigger and bigger and bigger, the function is getting smaller and smaller and smaller, right? It's approaching 0. Never crosses the x-axis though, right? It never gets negative. It just gets smaller and smaller and smaller and smaller. So we say that 1 over x is approaching 0 as x is approaching infinity, right? To indicate this behavior, as x is getting very, very, very large, this function 1 over x is approaching the value 0, or back to limit notation, we could say the limit as x goes to infinity of 1 over x is equal to 0. We can talk about negative infinity as well. We can ask what happens as x gets very large in the negative direction, so we can ask about limits at negative infinity, but this is what the question is asking. This is what this notation is indicating. It's saying as x gets very, very, very large, right? Not approaching a particular fixed value as we had before, x approaches a. Now as x gets big, what does the function do? Okay, so sometimes it's very easy to evaluate a limit at infinity, right? 1 over x, just intuitively, if x gets bigger, 1 over x gets smaller. So that limit was clear, it was 0. And sometimes that's the way limits at infinity go. But sometimes it's much harder. For example, evaluate the limit at infinity, the limit as x goes to infinity, of this rational expression, right? 9x squared plus x plus 1 over 5x squared plus 3x minus 2. Well, now you ask, as x gets very large, the numerator here, 9x squared plus x plus 1, that blows up, right? As x gets bigger and bigger, this becomes huge, right? So the top is going to infinity. The bottom, 5x squared plus 3x minus 2, that's also blowing up. That's also becoming very, very large, right? It's also going off to infinity. And in the limit, they sort of compete against each other. The top is huge, that tries to make the function very big. The bottom's huge, that tries to make the function very small. In the limit, it's not clear what happens. And infinity over infinity is not equal to 1. And I can't say that. So here's the idea, or the trick, with these types of things. Take the fastest growing piece of the denominator that you see. Right? For a rational function like this, it'll be the highest power. So divide top and bottom by the fastest growing part of the denominator. I'm giving you a very general approach here that works for all types of different functions, but for rational expressions like this, by fastest growing, clearly x squared grows faster than x, right? One's a parabolic function, one's just linear. As x gets bigger, x squared gets bigger much faster than x does. Right, so for us, this is just highest power of x. And if I do that and I simplify it, it'll actually become clear. It'll become totally clear what happens as x gets large. So let's do that. Limit as x goes to infinity, highest power I see in the denominator, x squared. So we're going to divide the top and the bottom by x squared. One way I can do this is I can take the entire top and write it over x squared, but I'm going to take each individual piece and divide them by x squared. It looks a little bit nicer to write it like that. So that's an allowable move, right? As long as I keep it balanced, as long as I do the same thing to the top and the bottom, that's totally fine. Why did I do that? Well, let's simplify this. 9x squared over x squared, that's just 9, right? So this is just 9. X over x squared, cancel one of these x's out on the top and the bottom, and that's 1 over x. And over here, I can't really simplify, this is just 1 over x squared. Divided by, on the bottom, what do I have? 5x squared over x squared, that's just 5. 3x over x squared, cancel out an x on the top and the bottom, and I'm left with 3 over x. And then I've got minus 2 over x squared. So same function, written in a very different way, though, right? I've manipulated it quite a bit, and this manipulation now makes it very obvious what happens as x goes to infinity. What do I mean by that? Well, let's look at these pieces. 9 is just 9, but 1 over x, what happens as x gets big? We already agreed 1 over x gets big, that's going off to 0, right? So as x gets bigger, 1 over x is shrinking down to 0. 1 over x squared, that's 1 over 10 squared, 1 over 100 squared, 1 over 1,000 squared, that's also shrinking to 0. So the top, as x goes to infinity, the top is just going to 9 plus 0 plus 0. What about the bottom? As x goes to infinity, we've got 5 plus 3 over x. Well, as x gets bigger, 3 over x shrinks to 0. And minus 2 over x squared. It's a minus now, but that doesn't matter because it's still 2 over x squared. That's shrinking to 0. So the bottom is going to 5 plus 0 minus 0. As promised, it's no longer hard to see what happens in the limit, right? 9 on top, 5 on the bottom. This limit is 9/5. So this is the trick you'll always use. With these rational expressions, limits at infinity, divide top and bottom by the highest power that you see in the denominator. I gave you this very general technique, though, fastest growing part. Sometimes you've got ratios of exponential functions and stuff. You just choose the fastest growing function on the bottom and divide through by it. But in any case, this technique works for rational functions in particular. So pretty lengthy video here. We'll stop here. Thank you.